So, welcome to the second session of the Everyday Crypto track. I'll just introduce the speaker, Joachim Strömbergson, who's going to tell us about an open hardware security module called Cryptech.
Okay, thank you. My name is Joachim Strömbergson. I come from an IT security company here in Gothenburg called Assured. And I'm proud to be involved in an international open project called Cryptech, where we try to design and produce an HSM that is open, so that you can actually trust it. And now we'll talk about what an HSM is and why we hope that you can actually trust it. And this story is going to be quite a lot about black boxes and trust and control issues and quite a lot of tinfoil. But in some cases it's actually quite well deserved. So we start out with what an HSM is. It's normally a piece of hardware that is used in all kinds of places. And since it's called Everyday Crypto, normally you don't actually realize that you're dealing with an HSM, but they're used in all kinds of situations. Basically, every time you log into a bank for doing banking, for example, then you're probably having an HSM in the back there, protecting the secrets that, for example, your OTP generator is using. It's used to generate ID information for passports, PIN information, all kinds of authentication systems. Certificate authorities used it to generate their certificates and store their secrets, no least, and all kinds of these things. So we are relying on HSMs for a lot of things in our society, but we don't realize that they are actually there. And the normal thing an HSM does is key generation, key storage, quite a lot of crypto stuff. Some of them are crypto acceleration, but the really big thing is that can you generate really good keys, can you store them and take care of them and protect them against all kinds of really hard attacks. So they're everywhere around us. And an HSM looks something like normally like this. It could be a box like this. Quite often it's like a 19-inch rack that you put into your service, or it's a plug-in card. Nowadays, an HSM can actually be something like this, a chip inside your computer, and that's what's been used to sort of basically taking away your control of your computer. You don't own your computer because there's something in there that stores secrets and controls your secrets and can be used to protect content that you can't copy and stuff like that. So basically that's also an HSM, but it's inside your computer. And one thing to note is that there's a battery sitting right here, and that one there. And that's because these things are, if we're talking about black boxes, these are really black boxes. They are built to defend themselves against active attacks. They actually monitor themselves. If you put one of these guys into your rack and you arm it and put it in production, if you try to open it up, it will destroy itself. If you move it a certain amount of meters, it will probably destroy itself. If you shake it, it will destroy itself. If you try to raise the temperature, it will destroy itself. It really is a machine that is really built to protect itself from people trying to do stuff with it, and manipulate it with it. So we really have this situation where we have white boxes that we can open up and trust, or we have a black box that we sort of have to trust anyway. We talk a bit about why that is a problem. And just as an example, this is an old HSM, an IBM 4758, very common, it used to be, old PCI board, and you can see there's a PCI connector here, and there's this box sitting right there. And unfortunately, it's not me that actually took this apart. I would have loved to do it, but I love to take things apart. But you can see here is actually pulling it apart like that and flipping it over. And typically you see this black tar thing, potting, that is covering the whole thing inside. So you have this electronics inside with connectors. And if you try to take that some more of that off, you can see things like this. This is basically wires, thin wires in film going over. So if you try to punch a hole through it, it would quite probably hit something like that and it would take it. And these things here are strain gauges that can actually take it, try to bend it or move it, and you can have temperature detectors and stuff like that. And then finally you get into the meat of it. You got a normal AMD processor, and you got FPGAs, and then a custom ASIC stuff there. And if you think of it, we only go that far into the machine, because these guys here are also black boxes, and this is definitely a black box. What does those chips do, actually? So, we don't know what the machine really does. Normally, you just get the specification from the vendor. And typical vendors are like Thales, Gemalto, and IBM, SafeNet, for example. And you read the specification, and you say, that, okay, they tell you that you can generate keys that are really good, and you can use it for these and these kind of operations, and then you sort of have to trust that. And just this, normally there are hardware things. They're actually nowadays virtual HSMs, software HSMs, which is kind of weird. But so what do you do if you wanna buy one of these things? You have a really important and high value system and an application that you want to use. And these guys run into like 100k euros for a good HSM, and then you probably want to get 2 of them for high availability. So then you go to the governments, to NIST, for example, and SBI in Germany, and CSEC in Sweden, for example, and they will actually have this like the FIPS 140-2 standard, now 140-3, and common criteria series, and then you have testing institutes that take one of these HSMs and test it for you, and then they put one of these stamps like the CMVP stamp and FISMA and whatever, and that means that the government says that this is a good machine. So now you can trust it, right? You have a black box, and you have governments that have put it up. Okay, now this is a good machine, you can trust this. And then we end up with something like this, with dual ECG, which is a pseudo-random number generator used in, for example, the RSA B-safe token generators. And the secrets in those are generated by an HSM. And it turns out that the generator specified by NSA, and they actually paid RSA 10 million US dollars to use that specific generator. And it's backdoored. And here's another good example. This is Citizen digital certificate cards. Basically client certificates that you have on your card that you can put into machines, and you can provide an electronic identification. This is from Taiwan. And of course, it has been tested. You can generate the cards itself, keys itself, and has been tested with CC Innovation in Canada, and I think it was in Germany, and in Taiwan, of course. And then Daniel Bernstein and Tanja Lange started to look at the public keys that these things gave out. And it turns out that it was like 10% of the keys were the same. So probably not that good, but it's a good big CMP stamp on it. So this is a really good. We approve this machine. So basically, we have this chain of black boxes. We have this trust in layers and layers. And the question is, why do we trust this? And if we don't trust something like that, why not? We prefer to have something like control. I think I'm just going to do something like this. I'm going to jump to this one directly first. This slide is from our leader, Randy Bush. And this is the way he likes Comic Sans. He always uses Comic Sans. And this is how they present it. And due to Snowden revelations and the problems people have by trusting governments and black boxes, is that so you have basically Yayalko and Stephen Farrell, for example, and the old guys at IETF said that we really don't. We really need to have an open SSM, and we can assemble ourselves, and we can test, and then we can before we put it in production. So and this is not an IETF project. I'm going to show you some of the people that financing us, but we work for the internet basically. And the goal really is to develop an HSM that is open and testable. That means that all the components of it you should be able to download from us, or and either you manufacture them yourself and assemble your HSM, or you have someone that you trust, and then and you can test it as much as you want before you actually put it in production. So we will develop components, hardware and software components, and if we need to rely on components from other sources, then we try to use standard components. there are a number of fantastic security components out there, and we really don't want to use those because they are also black boxes with good approvals from governments. We use BSD license for all source code, both for hardware and software, and we try to and we use common criteria licenses for Creative Commons for all documentation. And one of the things that we try to do is to also not only develop the components, but also guidelines and test systems and tools to allow you to actually take an HSM, our HSM or someone else, and test it as much as you can. And then to be able to drive the development, we also have a couple of reference use cases. And those use cases are based on a lot of the people financing us. So it's quite a lot of people doing infrastructure mostly. It's not as much crypto acceleration as say DNSSEC, for example. And one thing, what's going to be the end goal? It's going to be a ready product you can go buy? No, probably not. We are developing boards, we're developing components, and we are assembling some of them, but we are not really doing this to be able to sell HSM as profit. But since everything is BSD licensed, just grab it if you want to do, and if you want to make your own HSMs and sell them, go ahead. And the good thing is that you can actually assemble, using our stuff, the idea is that you can be able to take our components and create an HSM that meets your specific application, not a lot of other applications, and that reduces your security targets. This is not a hobby project. We are actually getting quite a lot of financing from a lot of different organizations around the world. Some of them government, some of them private companies. We are looking for more sponsors, so if you're interested in sponsors, come talk to me and we can have your number here. And as I said, we have a few reference use cases that we drive the development with, and most of them is really, let's say right now it's quite a lot about but DNSSEC and Tor and some of the authentication like SAMA, for example. So we need to implement things like SHA-2 and definitely have support for PKCS 11 in here, and then of course the key generation. And structurally, we have something like this. We have something on board that is inside the security boundary. We have FPGAs that we implement all the performance, the high performance stuff of crypto, for example, and run generation. And then we have a software layer that, for example, implements PKCS 11, so we can have that, so you can actually talk to your HSM. So. I'm not going to go down into detail of all the components inside the stuff here, but basically we have something like this. That we have a CPU with a CPU with a software stack. We have PKCS 11 protocol handlers, and we are using CryptLib by Peter Gutma as a middleware. And the CPU and the software can talk to the FPGA, where we have things like the SHA-2 and the Kirby accelerators, and of course the random generator. And then we have a tamper detect mechanism that can be run on battery power. That can detect if somebody tries to do stuff with, with the machine, raising the temperature, opening up, stuff like that. And then if it does that, it can kill a very small memory, a master key memory. And that memory is used to protect all the other secrets inside the machine. And this is where you really start getting into interesting problems. You can buy really nice master key memories, or secure memories and key memories from Infinium, for example. And then you have to sign on a lot of documents and NDAs and stuff before you can actually get information. And then if that document has any relevance with reality, that's not an issue. But those memories can sort of protect you from remnants, let's call it. If you keep information in a memory for a long time, then it will actually stick into the memory even if you turn it off, so you can actually read it out if you're fast enough. But one of the things that we have learned on, there's so many interesting research going on this kind of stuff, is that this memory here is connected to a battery. And one of the things that we try to do is that if somebody opens up this, we try to kill the battery power for it. And the question is, how fast do you need to do that? And if you consider you have a big an adversary that has a big budget, he can probably buy a couple of these machines. And we were told that one thing they do is that they actually put a steel rod right into the machine. So you have a little cover, and they put a steel rod like that, and then you put a big charge, explosive basically, and then you shoot down your rod into the machine at full speed. So you have a couple of nanoseconds to actually goes through, and that rod is of course powered. So you can actually insert power before before you can actually kill the memory. So things like that. And we have actually spent quite some time on looking at how can you actually kill a memory like that. One of the people in the project, he spent a fair amount of time taking very small memories and then very big supercapacitors, and then charge them up and see what happens if you put a lot of energy right into a memory. Will it fry the pins, the wires inside the chip, or will it actually fry the chip? And we have some very nice explosive pictures of but some of the people in the project, we have people, okay, I can do this. In order to, because we are an open project, and we're developing this, and of course you need to trust us, or if we want to have somebody need to be able to trust us. And one of the things that we do is that we try to have a diverse team. We have people in the USA, we have people in Russia, we have people in Japan, people in Germany. We are trying to find people in China, for example, and we're quite certain that, and we have people that are very interested in our project and are participating from Israel and Brazil, for example, and we know that some of the people that are involved or sort of try to influence are probably related to government agencies in various countries, three-letter agencies in different kinds of. And we have one guy that's from Russia, and he probably works for the military secret service in Russia. And his solution to handling the master key memory is that you actually put explosives on top of it, C4, and trying to convince Google, for example, to actually put C4 inside of their servers. I'm not sure about that. But that's what we do in Russia. I'm actually thinking of have a lot of nice discussions, and because normally says I can say something, I can suggest the solutions, and it does not work. And okay, can you elaborate? No. So, but he really a lot of good contributions, and that too is really good. But we might not do it that way. And we have people from basically from the other side, and we're pretty certain that are working for other gigs in the US and Israel and Germany. So, but that's the thing that we really try to bring in people from all kinds. So you can say that this is not a Swedish project, this is not an American project, this is an internet project. And we need to be able to handle that people might have relations that I really don't want to talk about. But we try to be as open as we possibly can about who we are and where our funding comes from. And we work in an open development process. We use mailing lists, of course, for all communications. And a lot of discussions there, and all the documentations. And one thing that we do is that we do signed commits. For all the things that we check in, you can actually trace everything back to me, all the stuff I've done in the random generator, for example. You can trace that back to me. And in fact, since at least 1.5 years ago, I always sign all my commits, even to GitHub or whatever. It's just easy, just sign it.
Can you really sign a commit in Git?
Yeah, sure.
Yes, you
I
can.
just tags, you can sign and push it.
No, we can since 2 years or so you can sign.
Yeah.
Okay.
Sign commits it.
Yeah. GitHub just ignores it. I would appreciate that GitHub could actually show that because it's part of the you can see the digest for it, the signed digest for it. It doesn't show how but it really accepts me doing it. So. Sure.
One quick question. So you sign all your commits, but where do you store your key?
That's a good question. I have my.
Frankly, I store my key on my machine. It's on disk, so
Yeah.
because it's
Yeah,
it should be on smart card.
I have a small black box sitting in a USB port I take out with me, where I keep my secrets, and I trust that black box for some reason. But it's so another layer. And one thing that we when we started out doing this, we need to have something to start working on. And one thing we did pretty early on was to decide on using something called the Novena. And I have one here. So this is Bunnie Huang, famous for cracking the Xbox, for example, the security unit. He actually developed a laptop. This is his laptop called Novena. And it's running a quad-core ARM-based CPU on it here. And it's blob-free, not like if you take Raspberry Pi, for example. You need to have a binary firmware inside it to actually get it up and running in the correct clock speed. You don't have to do that in here. And since he's a hardware tinker guy that wants to do weird stuff, he decided to have an FPGA on this board. So if you look at here, here's the CPU under the heatsink, and you've got a Wi-Fi that you can remove if you want to, and you have normal CPU memory. It has a lot of ports. You have double Ethernet ports in your laptop. It's not very common. And right here is a fairly big FPGA connected via high-speed interface and low latency interface. And over here is a connector that's connected directly into the FPGA. And this is perfect for us because we want to be able to run our own software on the CPU and then be able to put in put things like the random generator and stuff like that inside the FPGA. And if we want to run a random generator, we need to have an entropy source, and hey presto, there is support there. And I'm going to talk a bit about more random generators, but I'm just going to talk about something that is one of our problems, or that we try to deal with, is open hardware development. Open software development today is, as you all know, is fairly well. It's fairly easy. We have good compilers. We have good GCC and Clang LLVM. We have debuggers. We have linters. We have all kinds of good tools. But for hardware development, it really is not that good. It seems that the hardware community, it has been at least, thinking that as long as I can get the tool for free, as in no money, at no cost, then hey, I can use it and I can do my stuff. That's more important than actually having open tools that I can work with and change and control. So there's a bigger problem there. You can find tools that you can do schematic designs, and you can do some simulation on say analog circuits using SPICE, for example. And there are some open and free tools for that. But what you see people use is something like Eagle PCB, for example, or Alcyon, which is a cheap tool. It's a cost tool, but that's what people use. So you can do your things like you can do your schematic design like this. Very nice, typical Eagle design. And you can do drawings like this. But often the file format is a typical Bob, not open. And then if you start looking at what we're using, we need to do this. We need to design boards. But we also need to design stuff inside FPGA. And now we're actually entering the black box again. And if you don't know, an FPGA is an interesting, it's a chip manufactured in high volume that instead of having specific circuitry like a CPU, for example, or a DSP processor or a baseband chip for a mobile phone, it actually contains blocks of logic and memories and then interconnects going between them. And all this is controlled by bits, by registers. So if I can just set different bits in the correct way, I can actually connect, for example, this block here to this block here, and I can say this is an AND gate, and I can say this is an adder, for example. And so I can take a hardware design that I write and I describe, and I can generate hardware. I can get the wires I need, I can get the logic I need. And the cost of it compared to actually doing this in an ASIC is something like 10 transistors per more than what I've actually used it for just writing an ASIC. So there's an overhead cost about 10x. So if you can build an ASIC that runs, for example, in 1 gigahertz, I can run an FPGA in something like designing like in 150 megahertz, and it's going to be 10 times as big in terms of size. But but thanks to Moore's law, you can actually buy FPGAs that are very cheap, that actually you can put in some, like taking 64, if you remember the Commodore 64, the home computer that I loved and still love, I can actually take like 100 of the CPUs inside of that and push it into the FPGA on that board. So it's quite roomy in there. Anyway, so we have something like this. I write this is the Galamo application for AES, for example. Very simple hardware design. And I can synthesize that into some logic. And then we map that into those elements, and then we place them onto the chip, and then generate a bit stream. But all this magic thing happens here is inside of a tool from the FPGA vendor. I can't see what's actually happening here. And what I can do is that if taking AES, for example, I can implement AES, put it into my FPGA, and I can take test vectors from the AES specification and see that it actually generates the correct values. And if you have ever implemented a site function, like as you well know, it's either totally broken or it gets the right value. There's nothing like near perfect value. It's going to be either totally broken or perfect. But the thing is, you don't know what the tool put inside your FPGA besides your design, right? So we need to be able. So how do we protect against that? And to be honest, we don't have a good solution for that right now. Right now we're focusing on getting the functionality in there. But this is one of the things that we really need to think a lot in the project. And there are things that we can do. We can, for example, decide that we're actually going to build our own FPGA inside the FPGA, and then load our own design into that FPGA. That's going to cost us something like 10 times more again, so we probably won't be able to fit that much stuff in it. But that's one way to do it. I played around a little bit. The problem is to be able to take a design like this and generate gates from it. Fairly easy. Getting an optimized implementation is really, really hard. And there has been some people doing reverse engineering on the bitstream format, so we can actually generate stuff like that. But you're missing the optimizers, and they're really crucial. So actually the case that, in fact, that it's right today, I would say that it's actually easier to build an ASIC, a full custom chip, than doing FPGA and be able to control the way down, or as close as you can get to physical reality. Okay, I'm going to spend a few. A little bit time on entropy and random numbers. We spent quite a lot of time on trying to generate random numbers because they are really the key. If you can't generate good quality random numbers, then like if you're going to do a DNSX signing, if you're going to generate public keys, key pairs, and everything hinges on that you actually have good quality keys. But what is a good key? And especially in embedded environments. This is an example of a bad one. This is Travis Goodspeed, amazing Travis Goodspeed. He a great hardware tinkerer. This is a chip from Texas Instruments, obviously, and they have something called a C stack, a SIGBee stack. This is a low range, short range communications protocol, and people generate session keys for AES using that. And so there's a random number generated inside that. And he actually took it and extracted data from it just to see how good it was. And it turns out that actually it repeats every 64 bytes. So, not really good. And so they fixed that. And the thing is that you have millions of devices using that. And it's when I'm out talking to customers and organizations about IT security for embedded, this is one of the things I really try to stress, that if you want to use something good, don't invent your own stuff. Try to use what's available, but test it before you actually deploy. And obviously, quite a lot of companies don't do that.
Does that mean that there were only 64 possible session keys that it would generate?
Yes.
Because it just depended on the offset in the random?
Yes, that is correct.
For all sessions?
For all sessions, all products, millions of devices, very secure. It even makes the Debian bug quite good. Yeah. And of course you know there's that key to really good security, having really good keys, and they are random numbers. Yeah. And you can do things like this. You can try to. That wasn't really. I think this projector doesn't show. This is supposed to be really good random numbers generated random, and this is supposed to be PHP random. And you can actually see the lines, right?
Yeah.
So that's things like lines going through stuff and repeated patterns. It's not, you don't want to see that stuff. But the problem we have is that, and if you start to look at what's going back to Shannon, is that we're talking about randomness and entropy. And entropy in this case is that unpredictable events in a physical system, a stochastic physical process. And normally you get something like this. This is random decay, for example, if you have a ready element. And people are actually building random generators using old smoke detectors, for example. You can do that if you want to. The problem is that we want to go from something like this to something like this, that you get uniform distribution with good values. And there are some, as I said, there's some really nice ones, like you had the lava lamp, for example, and you have cosmic background radiation and radioactivity. Yeah. And they are really good, as they're hard to predict, and they're also normally hard to influence, because one of the things with HSM is that we don't want to be able to easily manipulate the entropy source. So you can drive it to some, say, insert bias, for example. So you can go from having a really big key space to a few numbers. There's an amazing paper by people in Cambridge where they took an RF, a radio generator, a radio signal generator, and put it a couple of meters from an ATM. And they just by sending radio waves to it at a certain frequency, they could get it down to only generating 1 or 256 session keys. So that's an example of how to influence a random generator. The problem with these guys here is that they are you get quite a few bits of them. They're very slow, and they're quite hard to have something like this in your server, for example. So in computers, we try to use things like this, that we have look at network information coming from like time between packets, noise from microphone, and time of flights in a hard drive, for example. And that works fairly good, but what happens if you replace that one with an SSD? Do you still have a movement of the head that you can actually consider as an entropy, or not, right? And key. So we developed, there's something called avalanche noise. So noise in a transistor, there's based on, so you can get a transistor to make quite a lot of noise. It's fairly resistant to manipulation, and we could put that board onto the onto the Novena. And then, as you can see, we've done quite a lot of designs of this, or prototypes, and you get noise like this, and then you try to put it so you can get something like you get some levels that you can actually measure somehow, and then you try to digitize that. And it turns out that it actually works fairly well without doing much manipulation of it. And if you look at quite a lot of embedded systems, this is as far as quite a few of them go. So people say that, well, I bought this embedded system, it has a random generator. No, it probably has an entropy source. And if you look at, for example, in OpenBSD or Linux, for example, the random generator sitting in the URAN or what you can talk to the URAN looks a bit like different. It looks something like this. That you have something that collects entropy as those unpredictable events or somehow. And then you mix them up, entropy, in somehow, in sort of a mixer. And then you have something called a CSPNG that actually generates your random numbers. And this one is the one that generates all the stuff you need, and this one has to be really safe. So this has to be there are quite a lot of number of, and all this going from here to here. This is all predictable. This is basically algorithms, right? So if you you can predict what happens given this value here, a specific value, you can generate all the kind of values. And there's many algorithms that are random generators, but there are not that many that are cryptographically safe. One very common one is called a linear congruential generator. And if you can observe two values of that generator, you can figure out the states. You can guess or you can calculate all the other coming values from that series, and you can calculate all the old ones. So that means that if I can see two keys from your generator I can predict all the keys. So that's not really good for if you have a secure generator. So But there are some good ones, and normally we call these guys stream ciphers. And if you look at, for example, this is Intel Bull Mountain. If starting from Ivy Bridge, x86 family of processors, and going forward, Intel has provided an instruction called RGRAM that you can read out random values for in very high speed. And it has this is their entropy source. It's basically two inverters that fight each other. So you turn the power off, and then you turn the power on, and then based on residue values and bias and whatever, they will either go to a logical 0 or logical 1. And you can read out that. And it turns off again and on, and does that with the frequency. So if your CPU is running at 2 GHz, then you get 2 gigabits out of this. It's really, really good. Yeah, okay. And so you got this here, and they got their conditioner or mixer using ASCBC, and then they have used AES in counter mode for doing the actual generator. And this might have anything, might be what's actually inside your CPU, or it may be by an algorithm that NSA has specified. We don't know. And if you look at Linux, for example, this is basically what Linux does. You can see it has CSPs and sitting right there, and it collects entropies and all kind of stuff. And this is what sort of, when RDRAM came out, Linux thought it was perfectly okay to actually just remove all this stuff and just put it like in here, basically, and replace them. That's a little bit of a mess up. Our TRNG looks like this in big blocks. And this is compared to other embedded systems. We really spend quite a lot of stuff inside the FPGA for doing this. So we have one source, entropy source, which is the avalanche noise sitting on the side of the outside, that's connected here. And then we have an internal entropy source based on ring oscillators, 32 ring oscillators inside FPGA running generates. And then we mix that up with using SHA-212, and then we have the SHA-20 CSPRNG generates numbers. And we can get something like 1 gigabit per second randomly out of this. And we spent a lot of times, months on testing it, and we have a big, and other organizations are testing it. And there are some suites they can do for testing, like Die Harder and ENT, and there are some government specifications that recommends how you do it. And the question is there, can you trust those? And I don't know. And then we've also done some development of tools ourselves. This is actually the entropy source, not the TRNG, but so anyway, we hopefully we can actually present the press release about the random generator fairly soon. It's the second random generator that has been going through all, based on 1.8 million tests. We were weak at 3, and we completed all of them. And that organization has tested basically all HSMs on the market, has been for the last 15 years. And so we're pretty proud. Actually seems to work pretty good. Yeah. But the status for the project right now is that we have a working implementation on Novena on IETF Prague this summer. We presented, we have Debian packages for it, so you can actually download, and if you trust us, or you compile yourself, and we have support. You can actually do DNS zone signing with it. We have complete PKCS 11 support. We have quite a lot of cores that we can put into the FPGA. Right now that FPGA is full, so we can't really put everything in there. We need to sort of take out some cores and adapt them for the application. We have the key generation software using the random generator. We can do key wrapping, so we can store the keys inside of it, and we can wrap them. We're using AS key wrap. We can do signing. We have noise source works, and we have everything running. And we have a server sitting right now that generates about 140 gigabytes of data every day. So if somebody wants to download big files and eat up a little bandwidth on the internet, we can do that. And if you trust that the data that we have there actually comes from our random generator, then you can go ahead and test it as much as you want. And right now the big thing we're working on is called the Alpha board, which is because one of the things with Novena is that it has so many things on it. It has a 0.8 interface and has this gigabit ports and has a GPU on it, and you can have Wi-Fi on it if you want to. And we really want to sort of shrink down into something that is our own, that we can control and don't rely on and particularly don't have a lot of kitchen sinks. You don't have, say, CAN interfaces and screen drivers, TFT drivers, for example, that we won't use because who knows what actually in there more. So we're working on the alpha board. It's going to be our first board. That also provides active tamper-proof support, so we can start developing those mechanisms. And to be able to get there as fast as possible, we are having this board right now, which is called the bridge board, which is so you can see what I'm actually holding in my hand. So we are moving from a quad-core ARM processor to an embedded microcontroller, an ARM M4-based core. And you can see here is actually the tamper mechanism sitting right now still even. And this is the entropy source, the avalanche noise source. And if you flip it over, it's quite empty. The only thing you can find there is the connector to the Novena connector. But we can easily place the FPGA on this side. So our HM would be something like this probably in size. And so right now we're having this one, so we can connect this to the Novena, and we can run software on the put cores inside the FPGA, and then put software on the CPU on this one, so we can integrate those things and see if we can debug that and get it to work. So we have like two CPUs talking to the same FPGA right now. And so I'm using this one as a noise board right now. So the alpha board is going to be, go back to this one. We have something like this. We have entropy sources, and we have master key memory that we can kill, and then we have our CPU, and then we have the whole temper detection mechanism. That's going to be developed. Yeah, we have C4 over here, but I'm not sure it's going to be needed. If somebody wants to do that, we can provide. And the thing, and the FPGA here is, and that's one thing also that we try to use open source tools as much as possible, and we don't want to, in order to be able to let people actually be able to use this much, we don't want to incur cost as well. So the FPGA that's going to be in here is going to be something like 10 times the size of the FPGA on the Novena, and we've chosen it so you can actually develop for it using tools that you can get at no cost at least. There are bigger FPGAs, but then you start having to pay actually for the design and development tools also. And just a few challenges going forward. Securing the hardware path. I'm talking about the tools there. But also securing the software path. We need to be able to audit that and also audit all the stuff that we've developed. We started doing some audits, but we need to do more of that. Fighting complexity, getting rid of a lot of kitchen sinks. Side channels. I don't know if you know, but you can actually figure out quite a lot of stuff about crypto hardware and software just by looking at how long they take to execute and power stuff like that. And we haven't actually looked at that much of that yet. And getting the alpha out early, 2016. And just an example of what we mean kitchen sinks. This is an ARM Cortex M4 chip, a CPU. And you can see here it's got a CPU, and you've got a floating point unit and stuff like that. And you've got CAN interfaces here, and you've got LCD controllers and motor controllers. And that's because we try to use general purpose microcontrollers, and they come with all this kind of stuff. And some we would like to sort of move forward to something that is basically just a CPU that we use. And just to finish off, the Cryptech project is cool, and it's not me saying that, it's actually that guy saying that. So if you want to hear him saying that, it was a good surprise for us. This was at IETF 93, they had this video conf with Edward Snowden. And he just said, oh, by the way, the Cryptech project, it's cool, very cool guys. So it was a quite cool moment, actually. So that's us. And if you're interested, come join us. If you go to that link over there, you will not get a working certificate. That's on purpose, and we can discuss why that is later on. But we have mailing lists as well, and we have all the source there if you want to look at it. And if you want to talk to me, I'll be here, and you can mail me. Okay.
So I guess there might be time for one or two quick questions.
Yes.
Have we been looking at interactive proofs and zero knowledge proofs for hardware verification?
Not that much, no. That's a good point. Yeah.
Yeah, given that you use Peter's scriptlib, did you look at Peter's own HSM stuff from quite some time ago? Then you worked on this hardware.
Yeah.
So it has some relevance.
Yeah, we looked at it, and we decided to go another way. And Peter is actually quite involved in Cryptech, and sometimes he agrees with us. Which is not that bad. I mean, there's a lot of people have no ideas and strong opinions and something. Yes.
On top of strong opinions, it's sort of flame-baiting question. Why the choice of BEC over for
We can take that on lunch, but let's put it this way: the project is run by people that was involved in MIT long before they like BSD and I like BSD, but we really want to be too close. There are people working in this project that actually went to school with Stalin. That might be a reason.
Right, that's all of what we have time for, I'm afraid. Will you? Where can we find the explosion pictures and videos?
Mailing list archives. I think there's quite a lot of pictures there.
Cool. Well, thank you again.